So we've previously looked at molecular spectroscopy and how we can use both UV and visible light to look at the electronic excitation of a molecule, as well as using infrared light to look at the vibrations within the molecule. And now we're going to turn our attention from molecular spectroscopy to atomic spectroscopy. So we're not concerned with bonds, we're concerned with the elemental composition. And just like we have with molecular spectroscopy, we can still do electronic excitation of individual atoms. Okay, now our Jablonski diagram here is going to look a little bit different. Okay, we have our ground state, and then we still have our singlet excited state, and we might have a triplet excited state, right? These are different electronic excitation states. And we increase in energy as we go up this diagram. Now, one of the things that you'll notice about an atomic or like a Jablonski diagram for atomic species instead of molecular species is that we no longer have all of these vibrational modes or rotational modes that give smaller increments between our different electronic states. We're simply looking at different electronic states like the S1 and S2 and S3, right? We can go up into these, but there's not vibrational and rotational excitation within each of these electronic excitation states. Now, just like with molecular species, with atomic species we can do absorption, and this is where we have the photon coming in, and we go from a ground to an excited state. Okay. We can also have emission. And this emission is simply once it's been excited in upper state, we can relax down and give off a photon. Now, we might talk about fluorescence, which is when we get excitation or when we get absorption plus emission. And this is the combined process of absorption plus emission. Get the right color. But what's interesting about emission in and of itself is that this can happen even if we have been excited in a manner that is not using a photon. So emission can happen with excitation using heat energy or collisional energy, any other form of energy that can get our electron up into the excited state can lead to an emission process. It does not have to be a photon. When it is a photon that has excited it to the higher electronic state, that's when we're going to talk about fluorescence. So fluorescence is this and that combined. Okay. Now, because we have these very defined states, these very defined electronic excitation states, and we don't have a variety of vibrational or rotational states to work with, what you'll notice is that the atomic transitions are going to be very narrow. So atomic transitions are much narrower bands of wavelength than molecular transitions. In molecular transitions, we might see broad peaks of 10 or 100 nanometers. Here we're looking at very narrow ones. You know, we might look at the change in wavelength or the distribution of wavelengths for a band being something like 0.001 nanometers. So these are very, very narrow, and we're almost always observing these atomic transitions in the gas phase. So we want to do gas phase analyses. Now we'll talk about one method for for solid phase analyses that's non-destructive later on with XRF. But for the most part, if we're looking at the atomic absorption, atomic emission, or atomic fluorescence spectroscopy, then we're likely looking at this in the gas phase. And so the next question is, well, how do we get all of our samples into the gas phase? And that's what we're going to look at in later videos, as well as in your assigned reading and your discussion sheet during this module.